shiver comes down now, shiver comes down.
So today we're going to go over a GDB tutorial, but before that, I wanted to give a review of some of the tooling that we've been exposed to or that we've actively used in all of the classes up to this point. Because coding, software development, software engineering, whatever you want to call it, is like carpentry, right? Or carpentry or woodworking, where the tools that you use to do the work are just as important as the work itself. So, for example, from day one, you were exposed to source control and software versioning, right? All of your labs are cloned from Git, which is a distributed VCS, a version control system. We've had version control systems for many, many years. It started out with CVS, I forget what that stood for, but then SVN came along, subversioning, and then finally 15, 20 years ago, I forget, Linus Torvalds created Git. and it has dominated the version control scene ever since. There have been other distributed version control systems, but that's the one that eventually won, right? Also, just to dispel a common misconception, that Git is not the same thing as GitHub, right? Git existed way before. I want to make sure that this is working. Yeah, okay. Git existed way before GitHub. GitHub is just a pretty website that uses Git behind the scenes, right? There are alternatives. So you can, like bitbucket.com or whatever it is. That used to be a better solution. In fact, that's where I host my books. That used to be a better solution than GitHub before Microsoft bought them out and then started making more stuff free. Another option would be Gitlab, right? That is a free and open source, completely free and open source solution where you can, it is a web-based version of Git that you can download the server, and as long as you've got the server to host it on, you can host that for free. As UNL students, you can go to git.unl.edu, and that is UNL's GitLab instance. You can log in with your Husker credentials, I believe, and have access to a GitHub or GitLab instance, excuse me. All right. So, why do we use it? Well, you have you might want one central copy, and then use it on multiple machines, right? It's a cloud-based backup, if nothing else. But it's much more sophisticated than that because you can track changes, right? You can blame, if a bug was introduced in some version, you can go back and track and have a completely auditable, right? Auditable, there we go, auditable paper trail or electronic paper trail of who did what, when did they do it, and maybe, hopefully, if they've got some good comments, why they did it, right? It's for convenience, right? For you right now, you're not doing any really complex systems, so it probably is serving as a cloud-based backup for all of your code. Don't transfer between, if you're working with a partner, for example, don't transfer files through email or Dropbox or something like that. You're engineers. You should start using engineering tools to do things. And one of those things with respect to software is Git, okay? You've also seen build systems. We've provided make files because we don't expect you to start writing your own building scripts. If you did the Java version of Lab 7 this last week, there is an Ant build in there. There was an exercise that it worked. I verified that it worked, but I've updated it since to make it a little bit easier to work with. But there was a build system in there for Java that's called Ant, right? And Maven is a package dependency manager. So every language, every technology stack is going to have some sort of a build system. In fact, that's an entire not discipline, but that's an entire job unto itself. They're called DevOps now, right? Development operations, where they don't write a single line of code. Instead, their day-to-day operations are writing lines of code in order to build the lines of code that are being written by the software developers. They manage the scripts. They manage continuous CI, continuous integration, where you take code that has been developed, you make sure that it passes all the tests, goes through QC or whatever, quality control, then goes on to a test server, and then eventually makes it to a production server. That entire process of continuous integration is handled and managed by DevOps. The last job I was in over 12 years ago now, we had about 100 developers, and two of them were, we didn't call them DevOps back then, but two of them were completely 100% dedicated to nothing more than build scripts and deployment scripts. So that is an entire job unto itself in a complex enough environment. We've also had even more exposure and familiarity with unit testing, right? We started out with ad hoc testing, where you just print something out, yeah, that looks good, let's move on, right? Then we moved on to more informal unit testing, where you were writing code to rigorously test your other code, right? And then we moved on to a formal unit testing framework, CMACA, or in the case of Java, JUnit, right? Those are the For Java, it's certainly JUnit is the de facto framework. For C, there are dozens. I chose CMaka because it was the easiest. Right? It was the easiest to install. It was the easiest to use, and that's why I went with it. Right? It was actually it's a fork off of an old Google project. I forget what. I think it was C Mockery. Google is notorious for abandoning projects, and they abandoned that. Somebody else took it up and forked it off and continued it, and they renamed it as CMaka. So it's got some pedigree behind it. Google. It started with Google. You've also seen static analysis tools and dynamic analysis tools. Static analysis tools are where you start out with your code, right? Before you even compile it, you use the compiler or you use a static analyzer to go through your code and find potential bugs before you even compile. The W-all flag or the W-extra flag. Sometimes there are extra, I agree. If I'm asking you for all of the warnings, right, I have to ask you for even extra warnings, right? No, I asked you for all of them. You should have given all of them to me. I don't know why GCC folks did this. There's also other compilers, the Clang compiler, the C-lang compiler, C language, right? And you can ask it to analyze your code instead of compiling the code. And sometimes 99% of the time you're going to get the same warnings in both of those. But sometimes you'll get different warnings that one compiler will catch and one won't, right? And sometimes you'll see warnings that, no, that's fine. I intended to do that. I know that looks bad, but it's lint. I'm going to go ahead and leave it in there, right? Because that's what I needed it to do, right? By the way, static analysis tools is a big business. There are even more sophisticated tools out there that you can take your code and you can contract with one of these companies. They'll run their static analysis tool through your code and report all these problems that are even more sophisticated. That can cost tens of thousands of dollars. Right? So there are companies that just build static analysis tools for other companies. Then we've seen dynamic analysis tools, right? Dynamic analyzers analyze code as it's being run. For example, Valgrind. If something is not caught by the operating system and results in a segmentation fault, then you can still run Valgrind, and Valgrind will say, you did something illegal here. Even though it didn't crash your program, it's something that you probably want to check out. On this line, I don't know why, but you've got an invalid read or an invalid write of size 4, right? A strong hint that you're doing something wrong with an array, right? An array of integers, right? You can also use it to check for full memory leaks, right? You can also use it to detect errors that don't manifest themselves, or if it does result in a segmentation fault, you can run Valgrind and it will tell you on what line it seg-faulted out on, right? So that at least you can look at that one line. And remember that you compile with the G flag on that. Something that we haven't looked at yet, but maybe we might do at the end of the semester, is perf testing. Perf is just short for performance testing, right? So, shorten up a word needlessly. These are called profilers. One of them, the one that we'll look at later, it maybe is gprof. That's the GNU profiler. Basically, it's not looking for faults in your program. It's not looking for segmentation faults. It's looking for inefficiencies. You can run a perf tester, a profiler, and it'll come up with a report that says, 90% of your computation time happens in this function over here. You might want to take a look at it because it's slow, right? And so you optimize that one function, and it goes from several hours down to a couple of seconds, right? That's what perf testing is all about, performance testing. You want to know where are you spending most of your computational time in this program. You can even generate heat maps that, it's hot over here and it's cold over here. It's hot over here. Pay attention to this section of code because this is the inefficient code. Right? What I want to focus on today, though, is debugging. Right now, in the context of Eclipse over here, I've shown you the debugger before, right? It's built into the Eclipse IDE. If you want to debug, all you have to do is set a breakpoint here, right? By double-clicking off to whatever line you want a breakpoint on, and you can go ahead and instead of hitting play, you can hit the bug play here, and it'll take you into the debugging perspective here, where you can you're paused at this line of code because there's a breakpoint over here. You can continue, right? Continue with the execution of the program. You can stop the program entirely, or you can step over each line of code, right? Dot, 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 right? Or if you've got a function, and I don't have any functions here, you can step into a function, right? And here, this is going to launch the printf function in the print stream class, right? Which does not belong to us, but we can go ahead and step into what's actually happening and behind the scenes in the standard library, walk through this, walk through this, walk through this. I'm just going to stop over here and restart it. There we go. And there we go. Now we're back over here. And you can take a look at variables over here, right? Well, what's the weight right now? 76.5. What are my arguments? Expand that out. The first argument is 76.5. The second argument is 175.25, right? You can you can stop the program and take a look around, right? That's what a debugger is. A debugger allows you to stop the execution of a program and look around and see what its state is. It is not proper to use what's called poor man's debugging, right, where you are using a bunch of printf statements everywhere. If you do that, and in fact, some of you saw that on your lab, that, oh, I got a bunch of output, 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 and then it segfaults, right? So it must be the function that just recently printed an error. No, it's not. It's somewhere completely different. And that's because output is non-deterministic. The way that output works is when you generate output, when you print something, it goes to a buffer, right? It's like a YouTube buffer, right? Where it loads up the video even though you are only watching a little bit at a time, right? All that stuff is stored in a buffer. It only makes it out to the screen when it decides to flush that buffer out to the screen and actually print it. So you could have a bunch of stuff in the buffer, right? And then an error occurs, right? And you've only seen part of the buffer, and there's a whole bunch of other stuff. An error occurs over here, and you never see it because you never saw all these print statements. It is completely unreliable. We call it non-deterministic, right? The problem could be somewhere else, and the only way that you're going to solve this is by either running Valgrind or using a proper debugger. And in the context of C, that's going to be GDB, right? GDB is a command line TUI, right? So you might have heard the term GUI, GUI, right? Graphical user interface. TUIs are text-based user interfaces, right? And by the way, the CS50 folks, or maybe it was VS Code, I don't know who, do provide this little debugger over here that you can run, and I think it is graphical. I've not played around with it, so I don't know how to launch it properly. But you can probably read about it and get a nice graphical debugger within the context of VS Code over here, right? Certainly with the desktop version of VS Code, there's going to be something that is very much like the Eclipse debugger over here. But I'm going to show you the TUI version of this, right? And again, a debugger, what is it? It's a program that simulates the running of another program and allows you to pause the execution, look around, view the variable values. You can even evaluate expressions, and you can step through the program line by line by line, right? I know that there's a problem around line 10. So I'm going to stop the execution at line 8, and I'm going to step through it slowly, taking a look at everything, okay? So how do we use this? Well, first of all, just like Valgrind, we have to compile with the G flag. The G flag, I think, is short for GNU debugger, GDB, right? That's why it's the G flag. Now, the reason that we need to do that is we need to preserve line numbers. We're not going to be able to step through the program line by line by line if all the line numbers are gone and the original code is gone. That's what happens when you just straight up debug, or when you straight up compile. It just translates it into machine code, and all the original stuff is lost. The G flag keeps metadata about your program alive in it, right? To run it, you just type gdb a.out, okay? And let's go ahead and take a look, right? Trial by fire here. Let's go ahead and just start, right? Now, here, I've got a buggy program here, right? Don't worry about it. If you see the bugs, don't shout them out, right? No spoilers here. But I've got a program that tries to create a random array of n elements where n is a command line argument, and it computes the average of them. By calling this function, that function, all it does is sums them up, right? So it sums them up and then divides by however many there are. And it reports the average, okay? So if I had, 5 random integers, it's going to be pretty easy to add those up in our head and determine if it's correct or not. Okay? Let's go ahead and compile this. And again, no spoilers, so I'm going to shut off all the warnings. The majority of the bugs here will be found by simply using a proper static analysis tool. But I'm going to shut that off because I don't want to see that. Right? I want to actually play around with these bugs and find them out by running the debugger. Also use the G flag. Right? And array.original, there we go. It compiles, so no syntax errors. But when I run it and, I need to provide, say, 4 command line arguments here. Yeah. Something's going on. Okay. I didn't expect that actually, but there we go. I was just slow. It was not an infinite loop, or it was not an inefficient loop. It was just slow because it's a browser-based development environment, right? So segmentation fault core dump. Right? What happened? To launch GDB a.out. Right? That launches this text user-based interface here. Right? Now I'm at GDB and I can start typing commands here. Right? I can go ahead and run my program, but we'll see just as before that the process and oops, where is it? With an error code of 1 operation. What? Starting program, where is it? Where's the usage? Oh, there it is. There we go. Usage. Because I did not provide command line arguments, it's going to immediately stop right up here and say exit 1. I'm not going to be able to reproduce that error. So if you've got command line arguments that you need to set, you can go ahead and use set args, and I'll set it to 4. If you had multiple arguments, 10, 20, 30, or whatever arguments you want to set, I'm going to set it to 4 here because I want to keep the array small so that I can do the math in my head. Right? I'll still might ask you to help me. Right? Okay, there we go, set args. Now I can run the program. And it comes up with computing average of nothing, and then the average is 0. That certainly does not look correct. Okay? So, but the program executed immediatly. Right? I wasn't able to stop it and look around and see what's going on. So much like Eclipse over here, you can set a breakpoint like by double-clicking on a line number that you want to break at. I'm going to go ahead and break at, let's say, line 24 here. Right? And again, you can probably do that graphically here using the debugger. I don't know how to do that, though, off the top of my head, though. I haven't explored that option. So I'm going to go ahead and set a breakpoint at line 24. Right? There we go. Now, this is my original code up here, but I'm not seeing my code down here. I want to see my code. I want to see the layout of my code, my source code, src. Right? There we go. And see that B plus right there? Right? Not a grade. It is a breakpoint. Right? So if I ran this program again, right, it would start the execution and then stop at the first breakpoint. And now it's a capital B plus. Right? All right, so I'm at line 24. I can start stepping through the program. Did we actually set the argvis of, the arguments? I'm going to go ahead and step through the program by going next, right? Next, next. Right? In fact, that's such a common command that you can just shorthand it as N, right? Next, right? Next, okay. Well, N should have received the value of the command line argument. Let's print it out and see what it is. Print N. 5, 4, blah, 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 garbage. What went wrong on line 31? No? Yeah. Well, that would be asking, is N equal to this thing over here, right? N is an integer, right? What is the thing on the right-hand side? Argvis of 1 is a character, right? So if I've got command line arguments, how do I convert them into an integer so that you can treat them as numbers? Right. What should it have been? A to I. There we go. That's my first mistake. All right, so I go back and fix that. Unfortunately, I would have to recompile. Some debuggers allow you to do what are called hotfixes, where you can change the code and then it recompiles in the background without having to restart. I have to restart. So quit out of GDB. Yes, I want to quit. Right? You can go ahead and clear the console here. Recompile. Remember the W flag. By the way, that would have shown up with the wall flag because you can't convert from a char star to an integer. And sometimes it's helpful to just run it to see if, well, did that fix it? No, it didn't. Okay, fine. Back to the drawing board. GDB a.out. Remember that we need to set our args. I'll keep it small at 4. Right? Layout. Now, you can go layout source immediately, which is probably what you want to do. But I'm going to show you that you can also do something else. Layout next. What's that? That's the assembly code. Right? So if you eventually do assembly in 230 or 231, right, you can use GDB to actually look at the generated assembly code. Layout next. You can layer the actual original C code along with on top of the assembly code. Layout next. You can actually look at the register values in the actual computer, or the simulated register values once it starts running. Unfortunately, the register values are unavailable for this. You'd have to do some additional setup here. Layout next. Right? Layout next. Right? And we're back to source. Layout source would have gotten me there immediately. Right? All right, so once again, let's go ahead. I know that everything is okay up until line 30, so let's just go ahead and break at 30. All right, and let's run this. Okay, so before n was incorrect, right? That it was just this garbage number. Next, print n. All right, that looks a lot better. Now it's 4, okay? Now I'm setting up my array. Next, okay, next. Let's print that array now. Let's see what we got out of that. Print AR. Uh-oh. What do you think 0, 0 is? It's a memory address that is, who's that? Null. That's null. So something happened here, right? Let's go ahead and restart the program because we're already in a bad situation here. We'll restart it from the beginning, yes. All right, now we're back over here. Next, next. Something happened in that function. Now, if I just go next, I'm going to jump over this line without seeing what happened in that function. So what I want to do is I want to step into that function like we did over here. If I just step over, step over, step over, it only goes in this in that particular context, right? If you want to actually step into a function, step into, right? Apparently, I couldn't step into the square root function, but you can use step into it. Over here in GDB, that command is step. Right? Instead of next, you step into the function, and now I'm at the random array. Okay. So let's make sure that we received n correctly here. You want 4 random elements. Okay, fine. Next. Okay. Next, next. So I'm going to fill this array up with 4 random elements. Well, what are they? Okay. How do I print an array? Let me try to print A. It's just a memory address. Why? Because int star is a pointer. Okay, well, how do I take a pointer and turn it into a regular variable so I can print it out? Dereference it. But that's an array. That only gives me the first element. Right? You can print, each element. Array sub 1 is, okay, that got the random value 8. That got the random value 0. Maybe we're not there yet. We're only at the print I. We're only at the second iteration of this, this for loop here because I is only 1. Okay, so next. Next, print I. Now we're on the 3rd iteration. What was that print A sub 1? It should be 8. Print A sub 2. Okay, that received a random value 1. Dot, dot, dot. I don't want to have to print each one out. Here's how you print an entire array. Dereference it and tell GDB how big it is at 4. Right? Because I know that it's going to be 4 elements. Okay, that looks good. Print A at. Now I know that 4 is stored in n, so I can also use that variable n instead, right? If I don't want to keep track of the size of my head. Okay. Next, next, next. We're about to return here, so let's print out what we're about to return to the calling function. 2811. Okay. So next. Next. Now we've returned from the function. What's the array? Print array at, and now in this context it's named ARR, and I expect it to be of size 4. Cannot access memory. Okay. Something's going on between that function, which looked okay, and getting back to the original function. Does anybody see what it is? Again, it's something that the wall flag would have pointed out to you immediately. No? Yeah. Yeah, what am I returning? Nothing. What should I be returning? The array, A. Now another bug here that's not going to manifest itself because I chose 5 is, well, here, let's save this first. And let's go ahead and quit out of this, yes. Recompile it, and let's go ahead and run this again. But I'm going to go ahead and set args to, say, 10. Okay, 10. Yes. All right, and I will say layout source. And I want to jump immediately to that function. You can break at a line number by giving it a line number, but you can also break at a function called, what was it called? Random array? Random array. It sets a breakpoint at the beginning of that function. Anytime that function is called, it will stop at the top of that function. So let's go ahead and run, and you see that it immediately stops at random array here. Okay? Now, let me go next here. Let's print out n. Remember, I think it was 10. Yep, there we go. Now you can print out an expression, right? How much memory am I allocating here? Print n times size of n. Now, what's the expectation here? 10 integers at 4 bytes each should be what? 40. Right? That looks correct. But take a little, but we're getting away with it here for a reason, right? It's just because it's a coincidence that n is also an integer. Right? Look real long and hard at line 43. Is there something wrong, something fishy, something that doesn't look like anything we've done before? Pay attention to size of n. Do we use size of on variables? Not generally. What should we be using size of on? On integer. Unfortunately, it didn't manifest itself as an error just because 4 and 4 are the same number, right? But if I wanted a random array of doubles instead, which would be 8, then this would fail, right? I wouldn't have enough space here. In fact, I'm going to put that to do. I'm going to do that to the afternoon class. Change this to a double. There we go. All right. So quit out of GDB and recompile. Remember, I've already changed it up here. Right? And so we're good now. So let's actually run it and see if it works. Right. Still segmentation fault. All right, fine. GDB. Now, if I don't set any breakpoints, set args to 4, I can just go ahead and run it. And it will eventually come up with, well, okay, there's a seg fault, and what line did it happen on? 66. I can jump down to 66 here and see, well, we're in the print array function, but we've already corrupted memory up to this point. This is why printf statements are not going to work. Before we even got here, we corrupted memory somehow. Right? And it's only manifesting itself as a segmentation fault when we actually go to print something. Right? So once again, let's go ahead and set a breakpoint, set break at main, and run. Yes. Layout source. Show me the entire thing here. Next. All right. And we fixed that return statement, next, but it's still giving us a problem here. Print array at, array at, what was the size, n? There we go. It's still null. Look real long and hard at lines 32 and 33 and tell me if you see something suspect. Where are we? There we go. So 32 and 33. Tell me, does this make sense? I want to compute the square root of 2. Congratulations, you did. Did you do anything with the result? What do you generally do when you call a function? You put it into a variable. Did we do that here? Nope. So what should I have done? Actually assign it the value. There we go. All right. So quit. Come on. Yes. GCC, GDB, layout, source, set args, 4, and let's break at line 33. There we go. And because I know that I fixed that issue, so run. There we go. So computing the average of, it didn't print. Why? Because the output is a buffer, right? We can flush the buffer. I forget how to do that. GDB flush output buffer. I don't remember all the commands either. Is there a way to clear? No. How to clear the input? Flushing the buffer in GDB. There. Had to go to 5. Nope. That's not it. So I'd have to look that up. Another piece of advice that I would give you is find a GDB, not a tutorial, but a cheat sheet, and print it out and put it up above your desk, and so that you can remember these things. Eventually, I'm going to give you a shortened cheat sheet in the notes here. Right? But let's go ahead and see if it prints out the array. All right, it's not going to actually print anything, but we can print it, right? Array at n. There are 4 elements in there. I see a sum of 14. 14 divided by 4 would give me an average of 3.5, something like that. All right. So let's say if we actually get that by stepping into the average function here. Okay. So next. Okay. Print the sum. 18. Was that the sum? No. What was the array again? A at n. 9, 1, and 4. 14. 18? How did that happen? Right. So let's go ahead and set a breakpoint at the average and rerun this. Right. Okay. Yes. Start it from the beginning. So, oh, that's right. I set a breakpoint before that. I need to get rid of that. So how do you get rid of breakpoints? You can clear line 33. There we go, and it's gone. Now I'm still paused there, but at least the breakpoint is gone, and I won't stop there again if I restart it. Now I don't want to go next, all the way to the next one, so I'll simply say continue. Continue to the next breakpoint, if there is one. There we go. Now I'm in the function. Let's see what kind of an array we have now. 1, 7, 1. That tells me that the sum should be 9, right? So what I want to do is, as I'm going through this, I want to print and see if I'm getting the correct sum. Is it summing it up correctly? But if I did that, I'd have to go next, print, next, print, next, print, next, print. What I'm going to do is I'm going to set a watch. Come on. There we go. Watch. I want you to watch the sum, right? Anytime it changes, it will report the old value and the new value. So that as I go through this, the old value is 4, the new value is 5. What was the array again? Print array at n. 1, 7, 0, and 4. It started out at 4, we added 1 and it became 5. Okay, that addition makes sense. But it started out as 4, what the hell is going on there? So on line 53, something happened. Or something should have happened that I didn't do. In C, an uninitialized variable has what value? So, what should I have started it out with? 0. Okay, fine. Quit. Yes. G. Layout. Source. Break at, what was it called? Average. There we go. Break at average. There we go. And run. Did I set args? 4. There we go. Run. There we go. Now we're at the average function again. I'm going to set that same watch variable, watch sum. Now before I start, let's go ahead and print it out once at least. Oops. Starts at 4. Print a at n. Did I not recompile this? GCC. Maybe I didn't. Oh no, because I just started up GDB again without recompiling. Sorry. Layout source, break at average, set args to 4, and run. Right. Print the array. 8605. Print sum. We're correct. Come on. What the hell? Remove a dot out. Yes. GCC. I did change it, right? I changed you. Make absolutely sure. All right. Layout. Source. Set args 4. Break at average. Run. Print sum. Oh my God. Oh, no, oh, you know what? Now, okay. It is 4 because we haven't set it to 0. What do I do? Next. Now print sum. There we go. Duh. All right. So we hadn't actually executed that line of code yet. All right. So now let's watch sum and print the array at n. So we should see this update to 4, then 6, then 13, and then it'll stay 13. So next, 4, 0 goes to 4. Next, 6, next, 13. Okay, I'm convinced that this is working now, right? Next. All right, print sum. Okay, print n. And I'm about to return sum divided by n. I wonder what that'll be. I can print expressions, sum divided by n. And it'll tell you it's going to be 3. Does that sound right? Should be 3 point what? 3 point and some change. What's the issue here? Integer divided by integer is an integer. So what do I need to do? Typecast double. Right. Quit. And I think that was everything. GCC a.out 4. 10, 12, 22 divided by 4 is going to be 5.5. Now, it looks like I've taken care of all the bugs. I have taken care of all the bugs. But it still could be possible that I'm doing something illegal or invalid, and it's just not manifesting itself as a bad output or a segmentation fault. In that case, you would still need to run valgrind to see if everything is still working. Valgrind, a.out. 0 errors, 0 contexts. Wonderful. So valgrind couldn't detect anything that went wrong. I can't detect anything that went wrong because it looks like the output is correct. My ad hoc testing here. The only other thing to do would be to write more unit tests and make sure and have even higher assurance that everything is correct. Everything is correct. Everything is correct. Okay. All heaps were free. No leaks are possible. Excellent. I find that hard to believe. Did I actually free it? I didn't free it. Are you sure? Whatever. I don't believe you at all. I would need to free array. Whatever. Did I free it somewhere else? Nope. Okay. No idea why you're not reporting that as a memory leak, because it is a memory leak. Yeah, I don't believe you at all. I know that it's a memory leak. I'm not freeing this at the end. That is definitely leaked. It might require full. I don't know. Let's go ahead and run valgrind with a full report of all possible leaks. Nope, still didn't come up with them. Oh, you know, duh. Of course it can't leak. I didn't give it any command line arguments, did I? If it actually does something here, it will leak these 4 integers, and there will be a 16-byte memory leak here. There we go, finally. Duh. All right, questions? No? Then, to review all the stuff that we did. Ooh. Hopefully the live stream is doing fine. Anyway, to run your program, so within GDB, you can run your program using run, right? You can set your command line arguments using set args, right? Set args to whatever you need to. You can view your code using layout source. You can go layout next to get to, say, the actual assembly code or registers or whatever, or lay them side by side. And by the way, I don't have much real estate here, right? And that's because this is all in one browser. In a real development environment, what would you be doing? You'd have at least 2 screens. And this is why developers have 2 screens, because they need the real estate. You're running a debugger over here. You've got your source code over here, and then you've got your YouTube over here that you're going off of, your notes over here, right? Your email over here, and then now you need 3 or 4 screens, right? My colleague Benita, she has one of those 4-foot curved monitors, right? They're getting kind of cheap, right? You can get one for like $1,400, maybe only $1,000 now, right? And so I have nowhere to put it in my house, and I prefer my desk to be minimal at work. So I mean, it's a dream, but you need a bigger desk first. And my desk is my chair sitting in front of the TV, so I don't really have anywhere to put it. Anyway, you can look at your layout, and hopefully you've got multiple screens in order to actually view everything. Right? Sometimes, now I've not experienced this since switching over to this IDE, this VS Code in the browser, but sometimes it can get garbled up and screwed up. You can always type refresh so that the entire screen redraws itself. Right? Again, you might not need that. I haven't needed to use that since switching over to the VS Code in the browser over here. You can set breakpoints. Right? You can break at a particular line 12. You can break at main, name a function that you want to break at, and it'll start at the beginning of the function. If you've got multiple files, and you're in one file, but you want to set a breakpoint in a different file, you say the file name, the source file name, then a colon, and then the line number that you want to break at. Or if there were a function, then you would name the function. Right? You can clear a breakpoint by using clear. For example, you can say clear 12 or clear main, right? Whatever your breakpoints are. You can print the value of variables or expressions. Right? Or expressions. Right? Print n times x, right? Something like that. Any C that you can actually write and execute and compile, you can run in GDB. It's a REPL, and it's not really a REPL. Which a repeat, execute, print loop, something like that. I forget what. Maybe that's wrong. But anyway, you can print an entire array of values as long as you know how big it is. And actually, you can use this as a trick. If you've got a really, really large array, like 1,000 elements, and you don't want to print all 1,000 of them, you can go ahead and say, well, only print the first 8. Right? And you can do additional tricks. If you do that pointer arithmetic that we talked about on Wednesday, if you do the manual pointer arithmetic, you can say, there are 1,000 elements. I want to know what elements 500 through 550 are. If you actually do the pointer arithmetic, you can jump to that memory location and then treat it like 50 elements. And so you can do whatever you want to do without having to, with the built-in functions here. Right? And of course, the most important thing is you can quit. Right? You can quit out of it and kill GDB entirely. If you've got a long-running program, or if you've got suspect that you've got an infinite loop, when you're running GDB, it will be in the infinite loop. You can go ahead and kill it by using Control-C. Now, on the command line, Control-C is going to kill out the entire program and kill the program. In GDB, it will simply just pause it. And at least it'll get you to the loop that is stuck in an infinite loop, right? And then you can go ahead and step through that loop to see what's causing this infinite loop here. You can set a watch on a variable. Right? Thought it was going to stay dark all day, but no. Right? And it'll tell you when it changes. When it changes, it'll tell you the old value and then the new value. The important ones that we looked at were also you can continue. You can go to the next line, or since that's so common, you can go ahead and use just n for short. You can step into a function using step instead of next. Otherwise, next will just go to the next line. Right? You can also do something really cool here. We covered this when we looked at the debugger in Eclipse, but you can set a conditional breakpoint. So for example, something's going wrong with this big giant array, right? 1,000 elements, but it's going wrong at element like 500 or so, right? I don't want to have to go next 500 times to get to the point where I think that something is going wrong. So you can break at, say, line 10, but only if the value of x is equal to 21. Right? That way you can set a breakpoint for a very, very large array. Right? For example, let's go ahead and go with GDB again. GDB, layout, source. And I'll set args to be 10,000 elements in my array. Right? And I want to go ahead and set a breakpoint at the average here on line 55. So I could go ahead and set break at 55, run, right? And refresh. There we go, refresh. So I did have to refresh. That's the first time I've had to refresh with this. And you were witnesses, right? So I was at line 55 here, right? Print I. I'm only at the first iteration here. Something's going to happen at at iteration 5,000. So next, right? No, I don't want to do that. Let's clear that breakpoint, clear 55. And what I'll do is I'll set a breakpoint, break at 55 if I is equal to 5,000. Right? Now continue. Continuing for 5,000 iterations, print I. Right? I'm in the middle of this loop now. Right? I didn't have to waste my time going next 5,000 times. And then when I get to 5,000 times, I accidentally hit one extra. Right? No, don't do that, right? Because now I got to start all over with 0. Right? Nope. Set a conditional breakpoint instead. And to do that, you can use any expression that you want. Any if statement here. If x is equal to 21 and y is less than 5, or foo is null, right? Whatever C expression you can write right here. Okay, any questions? No? Then later today on our weekly retrospective, I'll post additional information about the midterm. It's on Wednesday. You'll have 24 hours to do it. I just wrote it up and gave it to one of the LAs to examine, and you can expect it to be about the same length as the first exam, so it's not twice as long, well, scratch that. Since this is the honors section, I'll just tell you, you've got 3 functions to write in C. You have the exact same 3 functions to write in Java, right? So it shouldn't be that bad. Once you've solved it in one, it's going to be really, really easy to port it over to the other language. No questions about midterm? All right, then. I'll see you on Wednesday. Have a good break.